For most students, titrating a weak base with a strong acid is harder than titrating a weak acid with a strong base, even though the procedure are exactly the same. First thing we do is we always do a BCA table when a strong acid is added. We must write an acid-base neutralization reaction. The calculations must be performed in moles to determine how much of the acid or base is used up. Afterwards, we write an ICE table. The ICE table equation has to be a base dissociation equation. If you cannot dissociate the base, write a Bronsted-Lowry acid equation. You will get the same equation in which the water will behave like an acid. The calculations must be performed in molarity. So after you do the BCA table, you must recalculate the new molarity by adding up the volume and using the leftover moles. And number 3, you could write the Kb equation and do the products of a reactant and plug it in. It is a lot faster if you use the Henderson-Hasselbalch equation, in which POH is equal to pKb plus log of its conjugate acid, which is the HA, over the base, or the Bronsted-Lowry base. So in this problem, we're going to consider the titration of 100 milliliters of a 0.200 molar of CH3NH2, known as methylamine, by adding 0.100 molar of HCl. The Kb, or the equilibrium constant for the methylamine, is 4.4 times 10 to the negative fourth. We're going to find the pH for this titration. Initially, there is no strong acid added, so we do not need a BCA table. We're going to go directly into the ICE table. So we're going to take our base, and to help you out, we're going to react it with water. Here, the water will behave like a Bronsted-Lowry acid, and the methylamine will behave like a Bronsted-Lowry base. So the Bronsted-Lowry acid water will give a hydrogen, and the methylamine will accept it. Since it accepted a hydrogen, it is no longer neutral. It has a positive charge. Water lost a hydrogen, it becomes a negative charge. So it becomes OH minus. My charges, my matter, my atoms are all conserved. And I know this equation is correct. Why? I have a Bronsted-Lowry base, or a weak base, on my left side. On the right side, I have the OH minus, saying that the base dissociated, giving off the OH minus. Now I'm going to write my ICE table. The initial concentration of the methylamine was 0.200 molar. The water, we don't care because it's liquid state, so it's not part of the equilibrium. My conjugate acid is 0. My OH minus is 0. So minus X plus X on the right side. And to find the equilibrium, I add the I and the C. Now I'm going to write my Kb. My Kb is products over reactants, so it is my conjugate acid times the OH minus divided by my weak base. And I could plug this in, so this is going to be X divided by 0.200 molar minus X. This is equal to 4.4 times 10 to the negative fourth. The difference is greater than 1,000, so I could use the 5% rule. If you are unsure after you calculate it, you could figure out if it's less than 5%. So X is equal to 0.00938 molars. This is the OH minus concentration. So at this point, you could convert the OH minus to H plus if you want, or you could calculate the POH using POH. This is negative log of OH minus. This is equal to negative log of 0.00938 molar equals to 2.028. Since we want the pH, we know that pH plus POH is equal to 14 So pH plus 2.028 equals 14. So pH is equal to 11.972. Since there is no conjugate acid present, because it's an X, we don't know that value. We cannot use Henderson-Hasselbalch equation here. The only way we could do this is calculate the ice table, write the KB, and plug in and solve. Those of you that doubt the 5% rule, we could double check. So 5% rule is percent is equal to X here over the initial concentration, which is A minus, times 100. The X here is the OH minus concentration. So we know that was calculated as 0.00938 molar. Initial concentration was 0.200 molar times 100. This will equal to 4.69%, which is less than the 5% rule. So the 5% rule applies here. Now we have 20 ml of HCl added. So a strong acid is added. So we know we have to write an acid-base neutralization reaction. To do the calculations, we need to calculate this in moles. In the previous video, I used dimensional analysis. I'm now going to use the molarity equation. Either method works. I'm just showing you both ways. Find the one that is most comfortable for you and use that. Molarity equation is moles per volume. Molarity for the methylamine was 0.2 molars. This is equal to moles per volume, and we have 100 milliliter. I'm going to leave this in milliliters, and when I calculate this and I find my moles, I'm going to leave the volume in milliliters. If I do that, my moles I calculated will be 20 millimoles. If I don't convert my milliliters into liters, my moles will be in millimoles. And this is my weak base. I'm going to repeat the procedure for my strong acid. So if my strong acid initial concentration was 0.1 molar. This is moles. And again, I'm going to leave it in milliliters. So this becomes 2 millimoles of HCl. Now I'm going to write my acid-base neutralization. My base is the methylamine. My acid is HCl. So this becomes H3NH3 plus Cl minus. So if I simplify this equation, HCl dissociates into H plus and Cl minus, and the Cl minuses will cancel out. So my equation is CH3NH2 plus H plus EOCH3NH3 plus. And so we're doing the before, change after. The concentration in moles of the weak base is 20 millimoles. The HCl, we have 2 millimoles. And then the conjugate acid, we have nothing. So if I look at this, my limit is my HCl. I need to subtract the left side by the millimoles of HCl and add on the right side. This is going to be minus 2 millimoles. Minus 2 millimoles. This is going to be plus 2 millimoles. So if I do my math, this is 18 millimoles. 0 and 2 millimoles. So at this point, we know we have to do an ice table because the weak base and its conjugate pair exist. So the equation for the ice table is going to be the dissociation of the weak base. If that is difficult for you, react it with water. So this is going to be CH3NH2 plus H2O. Here is my Bronsted-Lowry base. My water is my Bronsted-Lowry acid. So my acid is going to give a hydrogen to my base. So this is CH3NH3 plus. It becomes a positive because it was neutral and it gained an H plus. and then the water becomes OH minus because it lost the hydrogen. My charges and my atoms and molecules are conserved. When I do an ice table, I must be in molarity or concentration to find a new concentration. So the new concentration of the base is CH3 NH2. This is going to be the leftover moles over the total volume because it's additive. So the total moles is 18 millimoles. The total volume is going to be 100 from the weak base ml plus from 20 mLs from the strong acid. I do not need to convert because the milli on top and the milli on the bottom will cancel out. So if you did the math correctly, you should get 0.15 molar. I need to repeat this for its conjugate pair. The leftover mole is 2 millimoles. The volume is still 100 plus 20. Doing the math, you should get 0.01667 molar. So at this point, I can complete the ice table. ICE. So the initial concentration of the weak base is 0.15 molar. The water does not count because it's liquid state. The conjugate acid is 0.01667 molar. Initial of OH minus is 0. The change, equilibrium, adding 0.15 molar minus X, 0.01667 molar plus X, and that X. So you know the next step is I need to write the Kb equation. Kb is equal to products of a reactant. And remember, water does not count because it's in the liquid state. So at this point, I could complete the problem, plug in. Since it's a difference of greater than 1,000th, I could ignore my minus x's. I could round these. So my x equals to 0.00395 molar. And in this case, this is my OH minus concentration. This is my x. Now I know I need to find pH, but I have POH, so I have to do negative log of OH minus. This equals to 2.403. So pH plus POH equals to 14. So pH plus 2.403 is equal to 14. So pH is going to equal to 11.60. The simpler way to do this is using the Henderson-Hutzenbach formula. POH is pKb plus log of its conjugate acid over its base. pKb is same thing as negative log of Kb. These two values I have on the side here, we calculated this above when we were doing the ice table. Since we already calculated this, we could just plug it in. We know what the Kb is 4.4 times 10 to the negative 4th, plus the log conjugate acid is this one right here, which is 0.01667 molar divided by the weak base, which is 0.15 molar. And when you solve for this, you will get exactly 2.402. So now we could solve for pH because we know pH plus POH equals to 14. So pH plus 2.402 equals 14. So pH is going to equal to 11.60, when I use the Henderson-Hasselbalch formula, it eliminates a lot of the steps I don't need. So if I go back, I could pretty much cross out all of this right here. I could cross out everything here. There is another way to do it, which is even faster using the Henderson-Hasselbalch formula. Since I am looking for pH, use the pH formula. pH formula for Henderson-Hasselbalch is pKa plus log of A minus, which is the conjugate base, over the weak acid. And I already know the weak base or the conjugate, and I know the acid. So all I need to do is find the pKa. And how do I find pKa? I need to find Ka. We know the relationship is Kw is equal to Ka times Kb. Kw is 1 times 10 to the negative 14th. This is equal to Ka times 4.4 times 10 to the negative 4th, which was given. So Ka is going to equal to 2.27 times 10 to the negative 11th. So this is going to be negative log of Ka, which is 2.27 times 10 to the negative 11th, plus log of A minus. A minus is my base. That's going to equal to 0.15 molar, divided by my acid, which is down here, which is 0.01667 molar, and you will get the same answer. You will get 11.60. And one other thing to note, if you are using the Henderson-Hasselbalch formula, you do not have to find a new concentration. You could use the moles that are left over. Why? Since it's a ratio of molarity over a molarity, the volume of both substances or species are the same, so cancel out. As I stated in the previous video, it's going to be moles over volume total. If I use the POH, this will be the conjugate acid divided by moles over the volume total of the weak base. And if you notice, the volumes cancel out, so you could even leave it at moles. And look at how much simpler this step is. And once you calculate the Ka, you don't have to recalculate it. You have it. So the only thing you need is the BCA table, and you are done. Now 65 mLs of the strong acid is added. We need to find the moles of the acid present to see how much of the acid and the base were neutralized. So I'm going to use the molarity equation. Molarity is equal to moles per liter volume. The molarity of the acid was 0.1 molar. This is equal to moles per volume, which is 65.0 mLs. I'm going to leave it in milliliters because I'm going to solve my moles in millimoles. 6.5 millimoles of hydrochloric acid added. So since a strong acid is added to the weak base, I need to write an acid-base reaction. This will create a conjugate pair. You can't write the acid-base equation, write it as a Bronsted-Lowry acid base. This is my weak base, which will be my Bronsted-Lowry base. My strong acid, which is my Bronsted-Lowry acid. HCl will donate an H. This is why it gained a hydrogen. And since it was neutral and it gained a hydrogen, it becomes now a positive charge. And what's left over is the Cl minus. Since hydrochloric acid is a strong acid, it dissociates into H plus and Cl minus. And you notice there's a Cl minus on both sides and they cancel out. So my equation again becomes CH3NH2 plus H plus yields CH3NH3 plus. So now we're going to do it before, change, after. the concentration of the weak base does not change. It's still 20.0 millimoles. The H plus we calculated as 6.5 millimoles, and there's none of the conjugate. Based on this equation, we know the H plus is the limit, so that means on the left side we have to subtract by 6.5 millimoles, and on the right side we must add 6.5 millimoles. And after is the addition of the two, this becomes 13.5 millimoles, and there's none for the H plus. The product side is 6.5 millimoles. So here we have the weak base and its conjugate present. We can write an ice table if you prefer. I'm just going to go directly to the Henderson-Hasselbalch equation, and I'm going to use the pH is equal to pKa plus log of the conjugate over the weak acid. And I'm using pH because they want the final answer in pH. You could also use pOH like we did in the previous problem, and then use pH plus pOH to 14. You'll still get the same answer. So pKa is the same thing as writing as negative log of Ka plus log of the conjugate base and the weak acid. We calculated the Ka, and it was equal to 2.27 times 10 to the negative 11 plus log. Since we are using the pH, the conjugate base CH3, since we are using the pH equation, A minus, or the conjugate base, is CH3 and H2, and the acid is going to be CH3 and H3 plus. It's going to be the opposite as if we were using the pOH equation. I plug this in. I could use the millimoles because the volumes cancel out, and I solve, and I should get around 10.961. Again, the volumes cancel out. If you want to add the volume, it's going to still be the same. I know the brackets means concentration. If I do the concentration of A minus, that is going to be 13.5 millimoles over the total volume, which is 65.0 milliliter plus 100, because the volume has to be additive. And if I calculate it for the acid, it's going to be 6.5 millimoles over 65.0 milliliters plus 100 milliliters, because they are additive. And if you notice, if I put it in a ratio, the volumes will cancel out. It is up to you, but this is the fastest way to solve for these problems. Now 100 mLs of that strong acid is added. We're going to do the same thing again. We're going to find the moles of the strong acid to see how much of the weak base or the acid is neutralized. So I'm going to use the molarity equation. Molarity is moles per volume, and the molarity did not change. It's 0.1 moles, and my volume is 100 milliliters. And when I solve for this, I get 10.0 millimoles of HCl. You could solve it to moles if you want, or you could leave it in millimoles. Just make sure you have the units correct. Since there's strong acid added to the weak base, I need to see how many moles are neutralized, so I need to write an acid-base equation. It is going to be the same as in the previous slide. So it's CH3 and H2 of the weak, and then HCl, strong. You're going to do a Bronson-Lowry acid-base if you can't write this, and you get the following equation. And again, the Cl minus will cancel out here, and you'll have an H plus only. So we're going to do it before, change after. The before moles is going to be the same as before, which is 20.0 millimoles. The acid we calculated is 10.0 millimoles. There is no conjugate. So my limit here is the acid. So I'm going to subtract by 10 on the left side and add by 10 millimoles on the right side. To find the after we add, so this is going to be 10. Our limit cancels out. There's none. And then on the right side, we have 10 millimoles. Here right now, this is a special case called the midpoint. Midpoint is halfway to the equivalence point. It's when the conjugate pairs have the same amount of moles. At this point, you don't even need an ice table. We're going to use the Henderson-Hasselbalch. pH is equal to pKa plus log of the conjugate pairs. The concentration of the conjugate pairs are the same. Log of 1 is equal to 0. So pH just becomes pKa, or negative log of Ka. So if I plug that in, that's negative log of 2.27 times 10 to the negative 11th, 10.643. So midpoint is a special case. The conjugate pairs, the number of moles of the conjugate pairs are equal to each other. It is halfway to the equivalence point. Now we're at the equivalence point. In the previous problem, we learned at midpoint, it was halfway to the equivalence point, and that was when 100 ml of strong acid was added. So at equivalence point, it has to be doubled. So we are adding 200 mLs of the strong acid, which is HCl. So again, since strong acid is added to the weak base, we need to calculate the moles of the strong acid added. We use molarity is equal to moles per volume. The molarity of the solution is still 0.1 molar. This is equal to our moles, and the volume I'm going to use is going to be in milliliters. 20 millimoles of HCl. The base we started with is still the same. Since a strong acid was added to a weak base, we need to do stoichiometry to figure out how much of the weak base or the strong acid has been neutralized. So we start with the weak base that was given, react this with hydrochloric acid as we did previously, and again write this as a Bronson lauric acid base. It's a lot easier. So the HCl will give, the weak base will take, and again HCl dissociates into H plus and Cl minus, so the Cl minuses cancel out. So we're going to do our before change after table. Our before concentration of the weak base is 20 millimoles. Our HCl we calculated is 20 millimoles. There is no conjugate, so that's 0. So here, if you notice, we have equal amounts of the weak base and the strong acid, so everything is neutralized. Subtract on the left side and add on the right side. Add the before and change. I have 0 of the weak base and the strong acid, and all I have left over is my conjugate. Since we have no weak base or strong acid at this point, we know this is at equivalence. So when I start my ice table, I must start my equation with my conjugate acid. My conjugate acid is CH3NH3+. I can't just dissociate this. Again, react it with water. Here, this will be our Bronson lauric acid. Our water will be our Bronson lauric base. So the acid will give CH3NH2. The water will take, so it will be a hydronium ion. And I know my equation is correct because I started with a Bronson lauric acid and I have H plus or hydronium ion on the opposite side. Make sure your charges are correct. So I'm going to complete an ice table, ICE. So to complete my ice table, I need to find the concentration of the conjugate acid. It's going to be the moles left over the total volume. Moles left over is from the acid-base equation table. So that's going to be 20 millimoles. And remember, the volume is additive. So we know that we added 200 milliliters of the strong acid and we started with 100 milliliters of the weak base. So if I calculate this, I will get 0.0667 molar. The millis will cancel out. So that is my initial concentration of conjugate acid. Water does not count. My weak base and the hydronium ions are 0. So now I'm going to complete the change in with minus x on the left side plus x on the right side. And if I add my equilibrium, it's 0.0667 minus x, x, x. So now I need to write my equilibrium equation, which is products over reactant. So this is a Ka. So my products are going to be CH3NH2 times the hydronium ion, or H plus, over CH3NH3 plus. I'm going to substitute in. So this is going to be x times x divided by 0.0667 minus x. We can assume that it's approaching 0 because we calculated Ka as 2.27 times 10 to the negative 11. Solving for x, you get 1.23 times 10 to the negative 6 molar. This is my x, which is the concentration of my hydronium ion, or H plus. So now I'm going to find the pH. pH is equal to negative log of my hydronium ion. So this is negative log of 1.23 times 10 to the negative 6 molars, 5.910. So the biggest thing to note is at equivalence point, the moles of the acid and the base cancel out, so there's no remaining and the conjugate pair exists. Now 300 mLs of the strong acid is added. So we need to find the number of moles to see how much of the weak base or the strong acid is neutralized. So molarity is equal to moles per volume. Molarity is still 0.1. The moles are what we're looking for, and my volume is 300 milliliters. This equals to 30.0 millimoles of HCl added. So again, we need to write an acid-base reaction to figure out how much is neutralized. I'm going to start with my weak base plus my acid, Bronson-Lowry acid base, my conjugate acid plus Cl minus, which will cancel out because this dissociates into H plus and Cl minus. Before, change, and after. My before concentration of the weak base is still the same. It is 20 millimoles. My acid recalculated as 30.0 millimoles. My conjugate acid is 0. So my limit here is my weak base. So I'm going to subtract on the left side. On the right side, I'm going to add. There is no more weak base present, and I have 10 millimoles of the strong acid, 20 millimoles of the conjugate. So at this point, we have two acids present. We have the strong acid and we have the conjugate, which is really weak. How do we know? The Ka was times 10 to the negative 11th. Here, we don't need to do an ice table. We could go directly to pH is equal to negative log of H plus, because even if I added this conjugate acid, because the Ka is times 10 to the negative 11th, it will have no effect. So I could just do negative log of the concentration of H plus, which is 10 millimoles over the total volume, which is 300 milliliters plus the original 100 milliliters, and this will equal to 1.602. So after the equivalence point, we could ignore its conjugate because the strong acid or base that is present will have a Ka or Kb much, much larger than its conjugate. So we could go directly into pH or pOH. Now we're going to plot our titration curve. The volume titrant is the strong acid that is being added to the weak base, and the analyte is the weak base. So we made these calculations here at certain points where HCl was added to the weak base, and those were the pH that we obtained. So at 0, we know that the pH is 11.972. At 20 milliliters of HCl added, it was 11.60. When 65 mLs of HCl was added, our pH was 10.96. When 100 mLs of HCl was added, pH was at 10.643. When 200 mLs of HCl was added, pH was at 5.91. And when 300 mLs of HCl was added, pH was at 1.62. So we're going to do a best fit curve. We know that when it was 100 mLs of HCl was added, this was